Assalamualaikum and how are you guys? Let us continue our topic on multi-phase system. Last time when we learned single gas, we learned about real gas and ideal gas. We only consider gas, which is a single phase. Here, in this topic, we're going to learn about multi-phase, which is liquid and gas at the same time. The first thing to introduce to you is the phase diagram. It is a plot of pressure versus temperature, and as you can see the different of phases of water, and here is the carbon dioxide. And along with the phase, there are a few points, and there are also a line that separate between solid and liquid, vapor and liquid, and vapor and solid. Okay, so this phase diagram basically a plot of one system variable, which is a temperature versus temperature or pressure. In this time is pressure versus temperature, that shows the condition which the substance exists as a solid, liquid, and gas. Okay, that is the definition of phase diagram. Let's see what happened to the property of the water when we increase pressure or we increase temperature. We start at point A, in which the water in a vapor at 20 degrees C and 3 mmHg. Remember, always consider temperature and pressure at the same time. So the water at A, the water vapor at point A, and then we compress or we increase pressure. Increasing the pressure will also say compress. Okay, we compress until point B, the pressure is increased, and the water vapor will start to condense and form a liquid. Liquid start to form. And when we further increase the pressure, we compress further. At point C, the water will start, all the water vapor will become a liquid. That is what happened when we increase the pressure. A water vapor will turn into a liquid water. When we increase the temperature, okay, when we increase the temperature from point C to point B, the water will start to boil. And then, when we increase further the temperature, all the liquid water will become a vapor. As you can see here, 100 degrees C is a normal boiling point of water. And when we increase further, all the water will become a vapor at temperature more than 100 degrees C. Always consider temperature and pressure. Okay, and then in this topic, it's really important to understand that at any temperature and pressure, what are the phases? What are the phase of that substance? Okay, and this is phase diagram for liquid. And then in this topic, you're going to take a look everything, the property, the phase of water. Okay, let's go to a bit detailed analysis on what happened to this phase diagram. The first one we have here is the vapor-liquid equilibrium curve. It separates between liquid and vapor. So this curve is called vapor-liquid equilibrium curve. Okay? In which the pressure is the vapor pressure of this substance at temperature T. Let's say here. Okay. Here we have P is the vapor pressure at this temperature. That means by this sentence. And then we also have boiling point, which is at point D. Okay. And then we have another line that separates between solid and liquid. This is called solid liquid equilibrium curve, and the value of temperature at any point along this line is named as melting point or freezing point. Okay, at particular pressure. Again, always refer to this temperature and pressure is always together. Okay, they just like a couple. They have to be coupled together all the time. Okay. Next is we have a critical point. Last time when we do some calculation, we really consider the value of TC and PC, which we can see in a table. Okay, the value of critical pressure and critical temperature we can see in the table B3, if I'm not mistaken. Check back B3. Okay, whereby beyond this line, the water and the vapor coexist. The water vapor and the water liquid coexist beyond this line. Okay. And then we have here a triple point, the point whereby the water will exist as a solid, liquid, and water vapor. Okay. And the last one is this line, which is separate between solid and vapor. It is called solid vapor equilibrium. And then along this line, any point, the temperature is called a sublimation temperature at that pressure, or we also call a vapor pressure at that temperature. Okay. Next, we're going to talk about how to estimate vapor pressure. Before we go to vapor pressure, what is vapor pressure all about? Vapor pressure is a measure of volatility. Volatility means the species tends to be vapor. It is in a liquid, but how high the tendency for it to be vapor? If the volatility is high, the substance tends to be vapor. If the volatility is low, the substance tends to be liquid. Or in simple word, we say a volatile component and non-volatile. Okay, I believe you already heard what is volatile. Okay, same meaning. Okay, but here we measure this volatility by using a vapor pressure. Okay, so later on we say it as a vapor pressure. We no longer using this word volatility. Okay, so the higher the vapor pressure at a given temperature, meaning the greater the volatility at that temperature. Always came together, pressure and temperature. Okay, pressure and temperature have to be together. When we say a pressure, when we say a vapor pressure must be at a specific temperature. Okay. And scientists already tabulate a lot of vapor pressure data. However, it came to a situation whereby the vapor pressure is not available at the temperature of interest. So they need a equation. They need a relationship to relate this vapor pressure and temperature. Okay. So that you can find the vapor pressure at any temperature. Okay. The vapor pressure is given by this symbol, P star. Okay. So how do they relate the vapor pressure and temperature? The first one, they are using this equation. Okay, this is called Claparian Equation. So it is this kind of equation. We have a vapor pressure, we have a temperature, and latent heat of vaporization together with a molar, specific molar in a gas, and specific molar in a liquid for that substance. Okay, because we learn more for water, so it is for water lah. Okay, and then when at really high temperature, really high pressure, the specific molar volume of liquid is no longer negligible. So some modification are made because we consider everything in a gas at really extreme pressure. Everything, the gas phase is dominant, so they substitute with PV equal to nRT last time. They do some modification, and then they came into another equation called Claparian Equation, and this is that equation. So B is a constant that different between one substance to another. Okay, this is the first equation. The second equation is named as Antoine Equation. It's simpler than previously. It's more simple because it's not that complicated. Just the difference between log and log. Okay, so it came with a table. Okay, there will be another table, which is table B4, whereby this table is specifically for you to use this equation to determine the water vapor at a specific temperature. Not the water vapor, the vapor pressure. Okay, I'm tergeliat lidah saya nak menyebut benda ni. Vapor pressure. Okay, vapor pressure at specific temperature. Okay, so we have A, B, and C, and then it's different from one component to another component. So you can just take a look. Okay, for example, if we want to find a vapor pressure for ammonia, we just go here and then we take all the value of A, B, C, and then make sure it is still within the range of temperature. Plug in everything in this, and we will get the value of P star, which is a vapor pressure. Okay, so there are two equations for this time being, and then the third one, they are using chart. Okay, this is called Cox chart. Okay, so this chart is not, the data is not as much as the table because it depend on this line. So each line represent each chemical, and how they do is they just drag at any pressure, drag until this line and read the vapor pressure. At any temperature, just go straight to the line of that chemical, then they go to this vapor pressure, so they can get the value of vapor pressure. Okay, that is how they do to estimate the vapor pressure. The next thing to discuss is about the Jeep phase rule. Imagine in our system, you have three species, A, B, and C, and then you have two phases, gas and liquid. Okay, So how do you want to explain about this system? To explain the system, you have to explain in terms of what are the variables involved. Okay? And then those variables can be divided into two categories, which is extensive variable and intensive variable. Okay, so the extensive variable is not depend on this extensive variable. Okay, just two, mass and volume. For the intensive variable, temperature, pressure, density, specific volume, mass and mole fraction. Okay, this intensive variable is a variable that we always consider. Okay, and we always, because it's really different at one temperature and pressure is different, and then the value of another, for example, the value of vapor pressure at one temperature is different, at another temperature and pressure is also different, and it keep on changing. That's why it's called a variable. Okay, and then this Jig phase rule is a rule whereby we have to calculate degree of freedom, meaning to say we have a system with a lot of phases, a few phases, and we have a few species. We have to calculate also the degree of freedom, just like you calculate previously. But last time when you calculate degree of freedom, you just list out all the unknown variable. But here, your variable is, the number of variable here is increased because you have to consider the number of species, you have to consider the phases. So it will increase your unknown. And here, you have to calculate the degree of freedom in which, using this formula, whereby the value of this, I don't know what we call this. This is the phases. How many phases? For example, here you have gas and liquid. So this is 2. And then C is the number of species. So here we have 3. And then we get the degree of freedom is equal to 3. So what this 3 means? This 3 means you have to specify this 3 value of intensive variable. For example, pressure, temperature, and it could be also the specific volume or mole fraction. Okay, if the degree of freedom is equal to 0, meaning to say you don't have to specify anything, or everything is already given in the equation. Okay, later on we see how to apply this. Okay, so this degree of freedom equal to the number of intensive variable that must be specified for system at equilibrium before the remaining intensive variable can be calculated. Okay, when we want to solve a mass balance for this system, okay, we really have to specify the temperature, the pressure, so that we can get extra data on the vapor pressure and so on. Later on we see the example. Okay, okay, next is about gas liquid system. Okay, when we have a gas and liquid at the same time, and in this condition only one condensable component, which is at that system, okay, regardless how many species you have, maybe you have A and B, okay, A and B or C, okay, so C is the most condensable one. It can condense at a particular process condition, meaning to say at one temperature and pressure, only one component can condense. That is C. For this, for example, C, Okay, for example, if you have 1, 2, 3 species, but at this temperature and pressure, only C can condense. Okay. Not everyone condense, just one component. Okay, so why we have to consider that kind of system? It is because if we want to separate, if we want to do a separation, okay, again, for example, we have A, B, and C. Okay, A, B, and C. Okay, and we want to separate C from the gas, right? So we have to make sure this C condense into a liquid phase so we can separate. Okay, so the example of the process, okay, that involve a transfer of a liquid to a gas phase is humidification, drying, and evaporation. I believe you know how this process work. Okay, and then a process that involve a transfer from a gas to a liquid is called condensation and dehumidification. Okay, the next thing is we're talking about the law. What are the law that represent that situation? Okay, it is called Roth's law. Okay, it is says that this is the definition. Okay, if a gas at temperature T and pressure P is contain a saturated vapor whose mole fraction is Y, okay, it has temperature T and pressure P with a mole fraction and it contain a saturated vapor pressure, and if the vapor pressure is the only species can condense when we lowered the temperature, then the partial pressure is equal to the pure vapor pressure of the system at that temperature. Okay, so I know it's really confusing to understand the statement, but what it states here is actually talking about this one. Okay, talking about this equation. So this equation is about vapor pressure. Sorry, it's about partial pressure. Okay, this is a partial pressure. And then this is a saturated vapor at specific temperature with a mole fraction. So it will be just equal. Okay, don't worry so much about this. You just remember this equation. Okay, I'm not going to ask you the definition. This is for you to understand. Okay, so this is the Roth's law, and here, and then there are cases whereby the partial pressure is lower than this vapor pressure at a pure component at a specific temperature. Pure component vapor pressure, okay, partial pressure, okay, this P is a partial pressure. Okay, this partial pressure lower than pure component vapor pressure at that particular temperature. Berbelit-belit kan? Okay, so it is called superheated vapor, and then the dew point is whereby the temperature when the vapor start to become saturated, and then later on I already draw for you to explain to you how the vapor, this dew point and everything. Okay, because it's also difficult for me to explain to you, and it's something that you cannot imagine. Okay.